This is section 7.1.4. We'll talk about projection matrix and its properties. We'll first revise 6.2.2 orthogonal projection slide 4, in which this figure presents projection of vector u on line V or on the subspace of V. This is u and this is V. Here, V, the subspace of V, is only spanned by a single line. And in the previous section, we learned that this is the projection of u on V, where basically we would drop a perpendicular line down, assuming that we are looking at the direction perpendicular to V, dropping the line down from point of u, and we'll get a point on V. This point would be the projection of u on V, and the vector is the vector along V. Under orthogonal projection, we have realized that this is the smallest error that we can ever achieve. If we try to land u onto any other place along the space of V, for example here and here, the error would be larger than this error. Let us try to interpret this point. This point is along vector V. It has a length determined by this scalar, because u is a vector transpose multiplying with V is a real number. The denominator of norm of V square is also a real number. So a real number divided by a real number is still a real number. It is a scalar. Hence, we can see that it is a vector V in the direction of vector V multiplying by a scalar to give us exactly this point, with the origin as the start of the vector landing here. Now, if this is a scalar, we can move the scalar to the left hand side, and this is what we'll do in this equation over here. The numerator V dot U is the dot product between V and U. It can also be written as V transpose U or U transpose V. In our example here, we have written it in this form. What about the denominator? The denominator norm of V square is equals to V dot V. So we see how we went from this equation on the left hand side to the equation on the right hand side. We are going to manipulate V dot U, the dot product between V and U vectors, which can be written as V transpose U. So this V is here. We have not changed a single thing. V dot V is also written as V transpose V. So basically, we are going to change the order of the braces. And now we have moved V transpose on the numerator, V transpose V on the denominator, multiplying by U. What is V transpose? Let V be a R n vector. V transpose is Rn multiplied by R1 by n. So actually on the left is n by 1. 1 by n means n by 1. 1 by n will get a n by n matrix. Multiplying vectors this way is called outer product. This matrix is a matrix of rank 1 because basically it is a single vector multiplying by itself to form a matrix. What about its denominator? V transpose V is 1 by n. N by 1 is 1 by 1, a scalar. What about this guy? U is also R, n by 1, a column vector. So remember, this is a n by n matrix multiplying by n by 1 dividing by a scalar. This will result in a n by 1 column vector, which is what we are expected because this is saying we are projecting u, a vector u, onto V space, and we will get back a column vector that is of the same dimension as V. Now we knew all this already in 6.2.2. What is new now is this interpretation. Projecting a vector u onto the space of V can be thought of as multiplying a matrix n by n matrix on a column vector u, which is n by 1. This matrix is very special. It has a name. It is called the projection matrix. It projects u onto the space of V. So once we have found the projection matrix, we call it P, we can project, for example, any vector, let's say y, onto V. It will be P times y. So by going through this process, we have now learned a new type of special matrix called the projection matrix. The projection matrix projects our target vector onto the space of our input. In this example, it is the input space of V. Now, what happens when our input space is not only a single vector, but a span of vector v1, v2, v3, and so on? Can we find also a projection matrix that does the same thing? The next slide will tell us how the projection matrix can be found for a space that is spanned by a few vectors. And in fact, you'll realize that these few vectors, we have collected them together and call it A. So we have v1 here, v2 here, and vn here. A collection of vectors, independent, forming a basis, and we are interested to project another vector on the column space of A.